Hello everybody, I'm back again to talk about titrations. We're in chapter aqueous ionic equilibrium, and we're going to focus today on titration of a weak base. Sure it's showing up. Weak base with a strong acid. So the sample will be a weak base. We say with, we mean that's the titrant. What goes into burette will be a strong acid. Let's talk about the system of interest. We have 20 milliliter sample of 0.105 molar ammonia. And we're titrating it with 0.125 molar HCl. So that's the molarity, and we also know the Kb of ammonia. Ammonia is a base, weak base, so it has a Kb. That's going to be equal to 1.8 times 10 to the minus 5. So we're given that. On the test, you'll have a table, or it will be written in the problem what the Ka and Kb values are. You don't have to memorize any of them. That's just a waste of brain space. So we have initial pH. So the way I would do it is write down the equilibrium of ammonia. So we got ammonia and water in equilibrium with the ammonium ion and the hydronium ion. Excuse me, that's wrong. Hydronium ion, and then what do we have? We have the OH minus, right? Still thinking of weak acids. So we have the hydroxide ion, right? So let's make an ice table here. Everything's going to be in molarities. I just write it right under the chemicals themselves in the equation. You can do it any way you like. We have 0.105 molar for the ammonia. We ignore the water. Initially 0 for the ammonium. And then we treat this as approximately 0. We ignore the autoionization of water. The big problem here, for some reason, when a lot of times, even though the problem might say, the problem may not say titrating weak base, it just might simply say ammonia and give you a Kb value for it, which tells you it's a weak base, and people start to write this as an acid when it's acting as a base. That's a very common problem. And on exams, I often put multiple part titration problems, and this could be very likely, it could very well be a problem type, on an exam. And people, a certain fraction of students tend to write this as an acid, even though it has a Kb given. So when you see a Kb, it's a hallmark statement that this is acting as a weak base. So we have a minus X here, a plus X, and a plus X. The E step is going to be bring it on down. So now we set up equilibrium expression. Kb is equal to 1.8 times 10 to the minus 5. I like to write it like that. I always write the chemicals in. I would write in products, NH4 plus, OH minus, you ignore the water in the denominator, so it's just NH3, products over reactants. We've got an X squared, we got 0.105 minus X. I'm going to use the small x approximation. If we check the percent ionization, we can see readily it's on the order of about 1%. It will actually be really good. So I'm going to treat this as the approximation. Again, you're welcome to do that full scale quadratically. But let's say out of a test and you have a problem like this and you got 4 or 5 components to it for a bunch of points, I wouldn't slow down and do that. I would do it out with the shortcut. So X here, this is another key step. I'll put a little asterisk here, is not H3O plus. It's the hydroxide ion concentration, right? So that's another thing people tend to make a mistake, and that's 1.8 times 10 to the minus 5 times 0.105 square root. I have to look what the number is here. 0.00137 or 1.37 times 10 to the minus 3 molar hydroxide. So you can't get the pH directly, you have to get it from, get POH next. That's how I would do it. And that's equal to 2.86. So pH is 14 minus that number, and that's equal to 11.14. 11.14. So if that's good. That means it's quite basic. And if you leave this, if you just think, if you're on a test and you forget this pOH and you do the calculation with the concentration of hydroxide, the pH shouldn't be acidic. This is a base, so you're missing a step. So think about physically what you're doing. And if you did want to check, like for example, I could ask you what the percent ionization is, and the percent ionization is equivalent to the error check to see how far you're off. So if you're, like we said, this rule of thumb, I'm using 5%. So let's see what we are. So that's the concentration of the OH minus and also the ammonia. You can interpret either way, times 100, and then I'm going to multiply it by the initial concentration, which was 0.105, and I'm just looking at this, seeing that this is about 1%. It's 1.3%. So it's well within the limits in terms of ionization to do the approximation. And that's also a question I could ask you on an exam to see if you can calculate the percent ionization. So you can use either ion. They're equivalent. The OH minus and the ammonium ion have equivalent concentrations. So that's the first part. We might use some of this information later, but I have to erase this because we're going to move on to other parts of the problem. I'll leave the reaction up for now. I'm not sure if we need it for the next step or not. Okay, looks good. Good enough to go. So now part B is let's calculate the volume of, this will be the volume of the acid, the HCl, to get to the equivalence point. So we do some calculations here we'll definitely use later, some of this information. So the big idea is that the equivalence point to millimoles of H3O plus is equal to the millimoles of the base we're titrating, which is ammonia. And you can think of this, the millimoles of H3O plus is the same as the millimoles of HCl, because this goes quantitatively in water to H3O plus and the chloride ion, or you can think of it as H plus and the chloride ion. Either way is fine, but what we can do here is for the volume to get the equivalence point, let's set up like an M1V1 equals M2V2 type calculation. So we have 20 milliliters of 0.105 molar H3O plus, because again, this is 1-to-1 with, should be a 125. I'm going to be getting confused with that. I don't know why I picked 105 and 125. Probably just wanted to use slightly different numbers so it wasn't just like, I want to make it like a realistic type problems where things often vary a little bit. And then that's going to be equal to, so we got, and I'm doing this wrong here. This is, no wonder I'm writing two different things down. We've got 20 milliliters of the 0.1, I was right, 0.105 molar ammonia, right? We're solving for the volume of HCl. So I was thinking correctly, I wrote the wrong chemical down. We got the ammonia, and that's going to be equal to 0.125 molar H3O plus times volume, right? There we go. So we're solving for that volume variable. So volume is going to be equal to 20.0 milliliters times 0.105 molarity. 0.125 molarity, so that cancels. We're left with milliliters. And what does that give us? That gives us 16.8 milliliters. That's the volume of HCl. To get to the equivalence point, we will use that number later in the calculations. We'll just put it off to the side now. Really, I put these in just, whatever order I'm thinking of at the time. So just retain that number. That's the volume calculation. So if this is confusing to you, just remember, it's based on M1V1 equals M2V2, which is not a formula I harp on, because it's just saying the moles on one side equal the moles of other. You can use it for various applications, including like dilutions and so forth. Here, what we're using it for is at the equivalence point. The conceptual, the chemistry of it is that the millimoles of H3O plus equals the millimoles of ammonia. The millimoles of the acid equal to millimoles of the base. You can think of it like that. So that's another part. I have to erase it, let you get a good look at that. So again, we made a little gaffe there, but the 20 milliliters is for the ammonia, and then the variables, what we're solving for is the volume of the acid. So move on. Go back, just retain that number. That 16.8 will come into play in a step or two, I believe. We'll see how I have it laid out here. So, step C, pH after adding. Let me put it down a little bit, so I'll work with the problem. Part C is the pH after you add 5 milliliters of the acid, right? So 5 milliliters of the acid. So let's do some math here. Let's figure out the millimoles we have. So we have we have 20.0 milliliters of 0.105 molar ammonia. I'm going to keep that as milliliters. That means I'm going to interpret this as millimoles per milliliter, giving me millimoles. You don't have to do this. You can do this in moles. If you can move this over, it's 0.02 in that case. I don't like that because there's just a lot of shifting around here, but do it any way you like. 2.10 millimoles NH3. Right, we have that. And then the acid, we're adding 5 milliliters of it. And the concentration of that is 0.125. I really have to watch myself because I have two similar but different numbers of H3O plus. And I'm going to, in my head, I'm saying HCl is going in water to H3O plus and the Cl minus. I'm not worried about that, but it's 1-to-1. It's a 1-to-1, so I'm automatically converting that. And this gives me 625 millimoles H3O plus. So that's a 6. The limiting reagent is the hydronium ion H3O plus, not the ammonia. So we're not going to do an ice table, we're going to do a stoked table, I guess we call it. We can call it we're stoked. It's a stoked table. It's got the same kind of ideas to it, just you don't have to put molarities in. We're doing a stoichiometric accounting. So we got 2 points, so this is going to be in millimoles. And again, you want to do it in moles, be my guest. 2.10 millimoles of that. We've got, let's change the reaction around. At this point, what we're doing is we're titrating with H3O plus, going to NaH4 plus, aqueous, and water. We're not going to worry about the water. So we added 0.625 millimoles of H3O plus, and we have 0 here. We're going to subtract 6.25, 0 minus 0.625. And on this side, we're going to add. So this is going to give us, of course, 0.625 millimoles of ammonium. We're going to get 0, of course. Something has to run out. The hydronium, and I can't do that in my head, 1.475, that makes sense. 1.475 millimoles of the ammonia. Look at what we have. If you don't see it, think about it for a second. To me, that is a buffer. That is a buffer. The problem will not say it's a buffer. That's a buffer could be two things. It could be something, or three things really. Something you design for cell culture, etc. It could be something that serves a similar purpose that, in a sense, nature through evolution is designed in your blood system or in your other tissues in your body or other animal bodies. Or it could be the composition of a system, for example, during a titration, where you end up having similar, within a power of 10 of each other, concentrations of a weak acid. This is a weak base, and it's conjugate acid. So what I'm going to do is I'm going to use the Henderson-Hasselbalch. I'm going to use the Henderson-Hasselbalch, and I'm going to erase this because there's a few steps I do have to do. This actually ends up being a simple problem, but there's a few steps with it. So we can set it up like, how did I do it here? So I use this formula here. POH is equal to PKB plus the log of I'm going to write it as the conjugate acid over the weak base. I'm going to do that because I have the KB. You could do it with analogously the pKa for pH directly. You could convert KB to Ka, calculate pKa, put it in here, and then flip these over. It will convince yourself you get the same answer. So I chose to do it this way. Do it the other way for proof to make sure that it works for you. Either way you like to do it. So I got the negative log of the KB given, and then I'm going to put in plus, and this is where it's easy to make a mistake. I can see myself doing this wrong. Conjugate acid is this, the ammonium, 0.625, and I'm going to talk about the step. And here, the ammonia, the NH3, is the weak base. Conjugate acid, weak base. Now, a big point is, and I've said this before, but I'll say it again, is because the ratio here is 1 to 1, concentration to 1 power, concentration to 1 power, the volume elements of the molarities cancel, so we can do this. I'm doing this with millimoles over millimoles. You could use moles over moles. The ratio will be the same, and it will be the same numerically as the ratio of molarity over molarity, because the volumes are basically dimensionally canceling. If you don't understand that, then convert this into molarities and put it in, but really try to understand that concept regardless of how you do it. I get, for the POH, 4.37, meaning the pH is going to be 14 minus 4.37, so we're looking at a 9 something, 9.63. 9.63. So we're, let's look at this here. We're before the equivalence point. We still got, we've consumed all the acid, and we have an equilibrium mixture with ammonium and the ammonia and the ammonium ion. I would expect it to be slightly basic. So you always know your pH scale. If you left it here, think about it. This is a base. We're not at the equivalence point yet. We're going to be basic. So not as basic as we were. Initially, what were we? We were a little bit higher than that. Initially, we were 11.14. So we've gone up a little bit. So I also show another method here. You can look at it on your sheet. There's two ways of doing this. And so again, the other way of doing it is using pH is equal to pKa plus log of weak base over conjugate acid. In that case, you'll get the same number. In that case, you have to convert Kb to Ka. So do it the other way and convince yourself you get the same number, which is 9.363. And I think that's good practice because it gives you a sense of confidence that you can do things a couple different ways. So we have that. That's good. So the next part of the problem is D, and D is the ones falling over. D is the, let's see here, the pH at 1/2 equivalence point. That's your halfway there. You've consumed half of the moles or half of the millimoles of the ammonia, NH3, and meaning that the millimoles of NH3 equals the millimoles of NH4 plus. You can think of it that way. You can also think that the concentration, molarity if you like that, that's good, is equal to the molarity of NH4 plus. They're both true statements because they're in the same volume, right? And so at that point, the Hedison-Hasselbalch becomes easy, and you can do it two different ways. I'm going to do it this way this time. So let's say you chose to say pH is equal to log of Ka, or I should say pK. I'll just put it in the condensed form. That's nothing wrong with what I'm writing. I'm just doing it the way I actually think about it. pKa plus log of conjugate base over the weak acid. From that perspective, this is the conjugate base and that's the weak acid. It's a perspective oriented, or you can use the pK POH equation. In that case, if you want to use this, let's say you said I want to do it with this equation. First thing is this term in either case is going to cancel out because the log of 1 is 0. So pH is equal to pKa. So in that case, the pKa, we need Ka. So Ka times Kb is Kw, which is 1.00 times 10 to the minus 14, right? So Ka, this is the Ka for the ammonium ion, is equal to 1.00 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5. That's the Kb given. I have to look in the calculator what this is. 5.56 times 10 to the minus 10, that makes sense. 5.56 times 10 to the minus 10 is the Ka for the ammonium ion. A table will typically give you, ammonia is a common reagent in the lab, will give you probably the Kb for that and not give you the Ka for the ammonium ion on a concise table. I mean, so we have here, this is going to be equal to negative log of 5.56 times 10 to the minus 10, and that's it. The rest of the other term goes to 0 because log of 1 is 0, and that gives me 9.25. It's more acidic than it was before if we had 5 milliliters, but not that much. It's went from 9.6-ish to 9.25. So that's good. That's a 1 or 2 step problem at the most. Get some easy points for it. I can even ask qualitative questions on that. So let's take a little look at this. This is the Kb, Kb equals Kw calculation. So appreciate that. You can do that with linked acids and conjugate bases or base and conjugate acid. You can't just do it arbitrarily. It's about 11:30 at night here. It took me about 4 hours to upload the last video. I'll let this one upload overnight. Not perfect, good enough. So the next part, pH at equivalence point. If I'm asking a problem on this, that's a definite. No doubt a question like this will be on an exam. Can't spell. Equivalence point, something like that. The EP is usually just put EP. That's a good reason. Let me see. We got plenty of time here. Let's do pH at the equivalence point. Okay, so we have to get first. Let's get the total volume. We have from before. We got a 20 milliliter sample. In the earlier part, we determined it took 16.8 milliliters. That was the HCl volume to reach it. And so what do we get from that? We get 36.8 milliliters. That's the total volume of the system. Let's put everything, we're going to have to do an ice method here. We're going to have the ammonium ion is going to be equal to 2.10 millimoles, because we calculated earlier that this is a 20 milliliter sample of 0.105 molar ammonia that gave us 2.10 millimoles. All the at equivalence, the first thing that happens is all the ammonia has been converted to the ammonium ion in water. There's a 1-to-1 conversion. So that 2.10 millimoles of ammonia we had initially is now 2.10 millimoles of ammonium. And I will divide this now. It doesn't have the same molarity as the ammonia did initially because it's swimming in a bigger volume. So I'm going to divide by 36.8 milliliters and I get 0.0571 molar ammonium. So that's the molarity. So what happens? We reestablish equilibrium. I'm just checking the clock here. We got about 5 minutes before I run out of time. These are long problems. So what happens here at equilibrium is the ammonium ion is now converted. Ammonia has been converted to ammonium. There's water. It reestablishes equilibrium with ammonia and generates out, it's acting as an acid. This is conjugate base now, the hydronium ion. Let's set up an ice table. Initial, we're doing this in molarities. 0.0571. Ignore the water. We've got 0 for the ammonia, and I'm going to treat this as approximately 0. We're going to ignore autoionization of water. Change. Minus X, plus X, plus X. Bring it on down. 0.0571 minus X, X, X. X is equal to, hopefully, can we see down here? Here we can see. Let's set this up. I'm going to need more space. I'm sorry. It's just a lot of stuff here. You have, hopefully, you can go back and look. The conditions are written down in the note set. This problem's in the note, so I'm just working it out in detail. So let's see what this is. This is a Ka is equal to whatever that number was before, 5.56 times 10 to the minus 10. That's equal to products, ammonia, hydronium over ammonium, which is equal to X squared 0.0571 minus X, and I'm definitely going to approximate it. Look how small Ka is. This is going to be X squared 0.0571, much like doing the quadratic equation for practice. That's squared. X here is equal to the hydronium ion concentration, and that's going to be equal to square root of 5.56 times 10 to the minus 10 times 0.0571, and that gives us 5.63 times 10 to the minus 6 molar H3O plus. So then pH is going to be equal to negative log of that and that's going to be equal to 5.25. 5.25. So we're just about out of time. I'll let you wrap up the rest of this problem on your own. I'm going to start solubility next. This problem will be worked out in note sets. The rest of it is just another addition of more volume step. I'll let you work that out on your own. I want to continue on to solubility, but from all the problems I've done, I think you had a good gist of how to do all these. So on that note, I'm out. Have a good night. Take care.